Okay, so good morning everyone. Let's start today's lecture. So today I'm going to cover tree-based methods, boosting, as well as random forests. I think all three topics you've probably seen in data mining. So if so, then we'll try to finish the class early, or we'll try to cover some nuances in these topics which you have not seen in the other class. Okay. So last time I was trying to introduce regression trees. So the basic idea of these tree-based methods is to have some sort of a recursive partitioning of your input space. So for a two-dimensional input space, basically we are just trying to partition. A partition is just a collection of disjoint regions. Okay, like. Okay, in this case, let me just do it this way. A partition is just a disjoint collection of regions which whose union is the whole space. Okay, so here it's region 1, region 2, and so on, all the way to 3, 4, 5, 6, and 7. And so the union of these regions are, let's say, J is from 1 to 7. Is the whole input space. Let's call it okay, I don't know, space S. And so let's say if you could partition the input space into regions, then any classifier regression function that you build using these regions, which define your classifier or regression function is as follows. So f of x is just sum over some constants Cj times an indicator function which says whether x belongs to that region Rj. Okay, j is equal to 1 to I guess a hat. So this regression function or a classifier is defined using these constants which are m in number, as well as these regions which are also m in number. Okay. So this is in general. This is irrespective of whether you're thinking of a tree-based method, tree-based partitioning, or any other partitioning. Somehow you get these partitions of the input space, and then given the partitions, this is your very natural notion of what the prediction function is going to be, whether it's for classification or regression. Okay. For classification, for example, you can think of these CJs to represent, let's say you already have these regions, then I can set CJs to be, for example, the average of yi's such that xi belongs to Rj. So just collect all the points, all the x observations which belong to that region, and then just take the average of the y's corresponding to those x's. Okay, or you can take Cj to be equal to the majority of all the labels that you see. So majority of Gi, I guess, such that Xi belongs to the region. Okay, very fairly intuitive notion of defining a regression function or a classifier, right? So then the question arises: how do I build such a classifier? And of course, how to build a classifier. You can always write down your loss functions, right? Let's say our loss function. Let's think of regression. Okay, and let's say the loss function is y minus f of x square. Then I can always try to minimize. So I'll write the generic objective here. Minimize over. Let's say we pick the number of regions to be. Okay, I have not used a notation, I think. Okay, so let's say I pick the number of regions to be m. Okay. Then I should minimize. So all the things which define my classifier are going to be region 1 to region m and C1 to Cm of sum over I is equal to 1 to n of the square law. So yi minus f hat of xi, where f hat is defined as above. Right. So this optimization problem, or this search for the right regions and the coefficients, would give me a classifier or here a regression function, right? And the problem here is that this has too much flexibility. How do I define these M regions? It's not clear, right? How do you, even for two-dimensional input space, you can chop the space into arbitrary number of M pieces, right? In any way you want. So there's too much of flexibility here, and because of which it's hard to find, it's hard to figure out what's the best, hard to find the best f hat, okay? Because f hat is defined in terms of regions and the constants in each region, right? So in order to fix this issue, so we restrict ourselves. Firstly to rectangular regions, or I would say in higher dimensions, I guess hypercubes. And second thing is we try to build the partition greedily. Okay. And last time I was just showing this in 2 dimensions. I was saying, okay, let's say we have a input region in 2 dimensions because it's easy to visualize. I said, let's pick one of the coordinates and split this whole input region into 2 parts. Let's say this is x2 variable, this is x1 variable. Let's say both vary from 0 to 1. Okay. Okay. So let me pick one of the coordinates. I'll tell you, and you have already seen this, but I'll repeat how this choice is made. So let me pick one of the coordinates and then split the whole space into 2 parts. So let's say this is region 1 and this is region 2. Okay, and then again, so that's first step. I pick the regions. I can given the regions, I can compute the constants that are supposed to be in each side. Right? I just told you that you can take the average for regression, or you can take the majority for classification. Now, why should I stop in one step? I can go ahead and for each region that I got, I can further split them in the next step into 2 parts. Okay. So maybe there's a part like this, maybe there's a part like that. So why is it that I'm getting a line segment here only till this point? Is because I'm first imposing at the first step that my region has been split into 2 parts. So this just means that first I split it into 2 parts. So therefore I have this part and this part, and each one, I guess this one, I'm splitting it into 2 parts like this, and this one I'm splitting it into 2 parts. Okay. So for the next step, the full region is just the part from the previous step, not the whole region, and that's why I have this distinction. Okay, I think I just made a mistake by skipping all the pages, but okay. So what I illustrated here is just a greedy procedure. I'm doing the split stage-wise. Okay, I'm first picking one coordinate, splitting it into 2 parts. Then for each part, I'm splitting each individual part again into 2 parts and so on. So 2 parts just corresponds to binary splitting. Okay, so that's the greedy part. And rectangular regions, because I'm just picking one coordinate and I'm just thresholding it to be greater or less than something. So I'll get basically line segments or lines or hyperplanes. Okay, I mean special hyperplanes. And so happens that this 2-dimensional representation can be equivalently written as a tree. For example, x1 sorry, in this case x2, for example, you check whether it is less than or equal to some split level t1 here, right? So let's say if it's less than t1, then it's in this bottom region. If it's greater than t1, it's the top region. And then depending on that, you have two parts, okay? And on each part, you again have a split. For example, x1 less than t2, and here maybe x1 less than t3. So let's say this is t3, this is t2, and this is t1, right? And the reason, one of the reasons, of course, was computational tractability. We said if we have arbitrary regions that we want to pick and arbitrary coefficients that we want to pick, this is too hard a problem. So we said let's restrict ourselves to rectangular regions and do it greedily. One of the byproducts of doing that is that we get interpretability. Okay, so we can actually eyeball, or if we do it in k dimensions. So in 2 dimensions, we are able to see a region and split it into parts, see the space and split it into parts, into regions. But in 4 dimensions, for example, you can't really visualize the 4-dimensional cube and think of how we are splitting the cube. Okay, but we can actually visualize that as a tree. Okay, a tree is nothing but a bunch of nodes. Okay, in fact, binary tree is just a bunch of nodes where each node has I guess 3 neighbors if it's an internal node. One you would call a parent and 2 children. Okay, and there are edges connecting them. So a tree representation completely characterizes this partitioning, even for higher dimensions, and that's why we are thinking of trees rather than actually visualizing the input space and breaking it into parts. Okay. So how do we build a regression tree? So we've already seen this. So if there is any inconsistency between what you've seen here and what you're seeing here and what you have already seen there, or if you have doubts, then please ask away. Okay, this is basically a review for many of you. So in regression tree, there are basically 2 choices. One is for you are at some node. Okay, so okay, let me think of the general step. So in the general step, you may already have a tree. Let's say somehow we got this tree. Okay, we're gonna we have a tree, and let's say at some point so let's say we are in this at this node. Okay. So this node corresponds to some region. Some region R0. Okay, let's call that region R0. And because we are recursively or stepwise processing or stepwise building our regression function, so we're going to try to break this into 2 parts, R1 and R2. Okay. And how do we break that? We have many choices. In particular, we want to break it using only functions of this form. So we're only going to find a j such that it is greater than some threshold t, or basically we're going to find an xj. Okay, we're going to find a j and a t. Okay, I've used s as a notation. I can use s. So we have p choices here. So we just need to find one of the j's, one j, one of the p input variables that we have, and a number s. Okay, so that we can break R0 into 2 parts. Okay, R1 and R2. So that's one thing that we need to do. And the second thing is, once we break it into two parts, I mean, I'll tell you how to choose the j and s. But once we break it into two parts, then we know how to put a number c1 hat and c2 hat there, which I just told you should be, for example, a candidate could be averages of the points of the y's of the points that are falling in those regions, right? And so let me focus on the first step, which is the critical part. Choosing the j comma s. Okay, so j varies from 1 to p, and s is a real number. Okay, let's consider s to be a real number, and it basically should belong to the range of the that particular input variable. Okay, so let's say this is a real number. So we'll just choose j and s such that a particular objective function is minimized. So what is that? Such that the minimum over C1 of, let's say, some L, okay, let me just note that, sum over xi in region 1 of yi minus C1 square plus minimum over C2 of sum over xi belongs to R2 of yi minus C2 square. So this number is minimized. Okay, so you have very few choices. So the choice of j and s affects R1 and R2, and because of R1 and R2 you get a number. Okay, so for every j comma s value you get a number, right? So try to get the number which is the lowest, this sum number. Okay, is that clear? So if you pick a j and s, so let's say naively, so how can you work with this? One procedure, one way to do it is pick a j is equal to 1, pick an s, which is some value, let's say that particular jth input variable is going from 0 to 1, so it falls in that interval. So pick an s 0.1. For that j 1 and s is equal to 0.1, evaluate this. This evaluation is easy because given the first coordinate and the threshold to be 0.1, you just count all the points on the left side of that threshold, and you'll get a C1 which minimizes the first term here. And similarly, all the points which fall on the right side of the threshold, you'll get a C2 which minimizes that number, and then you plug those C1 and C2 and evaluate this, and so you'll get a number, right? And so you do it for, let's fix the j to be 1, do it for 0.1, 0.2, 0.3, 0.4, all the way to 0.9 and 1. You'll get tons of numbers, and they'll all give you a score for your choice of j is equal to 1 and s is equal to some one of these thresholds. Similarly, you repeat it for every j. Okay, the p such choices that you can make there. So with the whole evaluation, you'll figure out that these scores are lowest at some j comma threshold combination, and that's what you pick. Okay, that's one way to think about it. C1 and C2 are average values inside the regions. So our prediction function. So let's think of regression. So our regression prediction function is just defined by the regions and the numbers inside each region, attached to each region. And I said if you chose in one step 2 regions, let's say you are at some node of this binary tree. A node corresponds to a region in this tree. So the root node is the whole region, okay, the whole space. So if you break a given node into 2 parts, then in each part you need to attach a number, right? If you break, let's say you are at some node and you want to break it into 2 parts, then you basically need that node initially was corresponding to some region and had a number, but now you want to break it into 2 parts. So you want to create 2 different regions, two regions, and attach one number to each side. So that number is going to be, I put hats here, but those are the two numbers, and those numbers can be computed as written here. Where do I write it? Yeah. So the numbers can be computed this way. Either you take the average of all the y's such that xi's belong to that region, okay, for regression, or for classification, you just take the majority vote of whichever class is the most occurring, in that region. Okay. So given the regions, computing these numbers is easy. These numbers that you attach to each region is easy. But finding the splitting the regions is the more difficult part, because now to split the regions you need to know what is the loss function. So what is the metric with which you are kind of defining how to split your region, okay, the original region into two parts. Okay. And so once I've told you these two steps, one I guess. Two steps, but one is just copied here. Once I've told you the steps of going from one region and splitting into two regions, you can do that for starting from the initial node and keep going over and over and over again. And probably you'll stop, naively if you think about it, you can stop when you only have 1 point in that region. So if you split it further, there's going to be a region where there's no point, so you can't really attach a number there. So might as well stop when you have 1 point in that region. But you can have, so that would be one option, but you can think of another way, right? So I don't want to go all the way when there's only 1 point in the final region in my node. I can maybe stop when there is less than 10 points in my region. Okay, so then I don't want to split it further. That's your design choice. Okay. Yeah. No, YIs are all your training data. These are YIs corresponding to the XIs which fall in that region. So we are just saying, I just want to know if I split my R0 into R1 and R2, I just want to know what is the squared loss in this case on each side. So if I break a region R0 into two parts, I still have two other things to decide, which is the constant numbers in each region. Let's say I decided the constant numbers to be C1 and C2, then I can assign how much is the loss in each bucket. I'm just saying pick the best ones, the C1 and C2s which lead to the lowest squared loss in each bucket. Okay. No, C1 and C2 are two numbers. Let's think of output variable as being one-dimensional. So C1 and C2 are two numbers, and in that region they are saying how far is that number far away from every other point, every other y value in that region, in the square loss sense. So I don't understand your question.
It is sum of two squares, right?
Yeah. So this one is kind of independent of that. So minimizing on one side has nothing to do with the minimizing on the other side, right? So I had R0 region initially, some node in my tree. I broke it into R1 and R2. So this had some constant, let's say some number that I had associated previously. Since it's an iterative step, I need to associate two numbers here, C1 and C2, right? So I'm just picking these two numbers by taking the average. Actually, I could have said, instead of writing this as an optimization problem, I could have just said just C1 is equal to sum over yi, such that xi belongs to that region R1. Okay, this is the same thing. The solution of this one-dimensional optimization problem happens to be this. Okay, so I don't have to write it in terms of optimization, but I wrote it that way because now you can change instead of square loss, you can think of absolute value loss or something else. Right? That's your choice. So I just took a choice to be square loss, and so you don't have to write it this way. I can just set C1 to be this. Okay, but I want to understand the quality of me choosing me making the choice of j, s. For that, I need to substitute this number there and compute the squared loss. Okay. Any confusion? So So I hope this is congruent with what you've seen in data mining class. Okay. Okay, so I just described, so you can stop the recursion. So it's called a recursion for those of you who are not from some CS type of background. Recursion just means you repeat these steps iteratively for every region that you see till you reach some stopping, till you reach your desired stopping situation. And the stopping situation is, for example, the region or the node has less than 10 points. Okay. So that is also, the criteria for stopping is also your choice. Okay, so at this point, once you stop, you already have a tree. Let's call it T naught. Okay. So this is just a notation. T naught is just representing a tree. And just to kind of touch back on the basic, tree is just a graph where there are no cycles. Okay, that's the definition of a tree. But all it just means is that you're just flowing. For example, in this case, we are only looking at binary trees. So every internal node has 3 neighbors, and every terminal node has 1 neighbor. Okay. So this node has 3 neighbors, and this last node has 1 neighbor. And the root has probably 2 neighbors. Okay. And so typically what happens is this tree T naught that you derived using the iterative procedure that I described earlier may be big. So typically in these types of prediction models, tree-based methods, including CART, they also try to do a post hoc, pruning. Okay. Pruning just means cut the tree into trim the tree. Okay. So to prune, again, you have to kind of determine which node. So pruning just means I'm gonna merge some of the nodes. So in the tree construction process, I had a region, I was breaking it into parts, right? 2 parts. Every node I was breaking into 2 parts, going into another level to the next step of the recursion. Pruning just means I'm gonna merge nodes back together. Okay. So again, it's not. Okay. So there is some procedure called cost complexity pruning. Okay. So there are many ways to prune a tree. Okay. So you can always remove the. So if you had let's say you had a tree like this. Okay. I can always prune the tree by saying I'm going to ignore the whole last level. So remember these 2 regions, their sum is this region. Okay. So I can delete these 2 nodes and I have pruned the tree. Okay. That's an example of pruning. But we are going to look at a specific type of pruning called cost complexity pruning. And for that, what we want to do is we want to find a tree which is a subtree of T naught. Okay. So find a tree which is a subtree of T naught by collapsing its internal nodes. Collapsing just means merge a node, okay? Merge two nodes. So these are internal nodes. For example, these two. Just merge them back. Okay. It's called cost complexity pruning because first of all we are restricting ourselves to trees which are subtrees of the original tree, and we're going to penalize for the size of the tree. Okay. So we have so when I said T naught may be big, all I'm saying is the number of nodes in the tree is too many. Okay. Let's say it's a binary tree, then the number of nodes, since there is a binary split at every region, I may have too many leaf nodes, as in the last terminal nodes. I just want to reduce the number of nodes in this tree. Okay. And I want, whenever I reduce the number of nodes, I just want it to be a subtree. Okay, this subset notation that I've used here, I just want it to be a subtree. It just means that I only want to kind of operate on the original T naught. I only want to kind of collapse the nodes in the original T naught. I don't want to recompute again smaller size trees. I don't want to build a tree again. Okay, I only want to trim, as in delete nodes, not really delete, but collapse nodes. Okay. And so I'm going to now specify the objective. The specifier is going to be the objective is going to be some cost with a parameter alpha for a given given tree is going to be equal to sum over little m is equal to 1 to the size of the tree. So size of the tree is just the number of nodes in the tree. Okay. So I'm going to use the set notation, like two vertical bars like this is the number of nodes in the tree. Okay, and then I'm going to use nm. I'm going to define what nm is, and then some qm of the tree. So I'm going to tell you what nm and qm are, plus some alpha times size of the tree. So okay, let's quickly understand the second term. The second term is saying, so the cost that I'm going to assign to a tree has one term which is directly proportional to the number of nodes in that tree. That term is kind of intuitive, right? So this is how I'm going to attribute scores to trees. Okay, and then I'm going to pick the tree which kind of balances out the size of the, it's getting penalized in terms of how many nodes it has. For example, T naught may have 100 nodes, then alpha times 100 is the cost for that T naught itself. And then if I collapse the last, collapse an internal node, okay, then I may have 98 nodes instead of 100 nodes. Okay. So that term is clear. So this first term is just saying first term is just counting the number of nodes that I have. So m is going from 1 to the number of nodes in the tree. So that's why we use the same notation. And for each node, I'm just counting the number of points in the tree. So this is just the number of training data points belonging to that region. Okay, because every node in the tree corresponds to a region. Okay, all I'm asking, if you think of the root node, all points belong to the root node. And if you think of the terminal node, some points belong to the terminal node. Let's just count the number of points that belong to that region. Let's call it generic region as m, little m here. And then qm is, we're just going to call it the node impurity function. Okay, just a fancy name. All it's saying is how good is that cm, how good is that? So in that region m, I had a number cm that had tagged onto it, that region, right? So how good is cm? Okay, let's call the region itself Rm. So QM is the function, which is node impurity function, and it's saying how good is that number that I tacked onto that region for that region. How good is that number? And one obvious thing that should come to your mind is that I can say how good is that number by just, for example, computing Cm minus yi, sum over I is equal to 1 to sum over all xi belonging to the region M square, for example. This is a goodness function, right? It's saying how good is that number that I associated with that region, and this is one way to kind of say that. Okay. And so all we are trying to say intuitively is that we had a huge tree T naught. So we had a huge tree T naught, and we are looking for subtrees of this tree by collapsing nodes, okay, such that maybe we have a fixed alpha. It's like a penalty between two things. One is how big is the tree. If the tree is too huge, then there is a penalty, additive penalty here. And if and for that given tree, I'm going to just count the node impurity value of every node in that tree. I'm just going to add these node impurity values scaled by the number of training points in that node. Okay, and I'm going to sum over all nodes. So it's just a quality metric that I'm assigning to a tree. Okay, and this should actually not be very unexpected, because when we're actually constructing the tree, we are roughly adding these things. Every time we have a region and we break it into two parts, the region has the Cm value. And so we are actually, so in the construction, if you saw, we are using some function like QM to break the region into two parts. So R0, when we broke it into two parts, we actually use a square metric, right? And so there's some efficient way to compute this, but let's not worry about that. Just understand that the tree construction is something that you can do, and you can always stop this tree construction when you have some defined criteria, like the minimum number of data points falling into my node should be at least 10 or something. Then only I will break the region into further parts. If you have such a stopping criteria, then you will have some tree. Let's call it T0. You may wish to prune it if you think it's too big, and if you want to prune it, then you can go back and collapse nodes using this criteria, okay, for some alpha. And so this is a degree of freedom, a choice that you made. So again, you may want to do cross validation to pick the right alpha. Okay. Is there any confusion? You've already seen this, so but there should not be any contradiction. Okay. Okay, so let's look at classification trees. Okay, classification tree, and there's going to be a couple of minor changes. We need to kind of replace squared loss while constructing the tree, as well as the quality metric that we use while pruning the tree. Those are the only two things where you want to modify. So for that, let's first define another thing, which is the p hat mk. So let's say we are looking at region Rm. Okay. So for that region Rm, I'm going to kind of define k numbers. Okay. K is equal to 1 to capital K. And these numbers are just going to be nm is just the number of points in number of points in my training data falling into that region. It's just a scaling thing times the sum of xi in that region, all the points falling in that region, of an indicator of whether gi is equal to k. Okay. All I'm saying is, okay, I have some number of points, 10 points falling into this region. Maybe 3 of them are of class 1, 2 of them are of class 2, another 5 of them are class 3. So that's, it's basically 3 by 10, 2 by 10, and 5 by 10. Okay, that's 3 numbers that I'm putting in, using for each region. Okay, so that's the difference. So with regression, you're just looking at an average 1 number, and with classification, you're looking at 3 numbers if there are 3 classes. Okay, and so these are just numbers I just defined. If for any region I can define this. So if you are again at region R0 and you want to break it into R1 and R2 in the tree construction process, right? Then you had these 3 numbers p hat mk, and you're just asking p hat mk for the first region and p hat mk for the second region. You can compute this by just doing the summation, simple averaging, right? And so again, your choice is going to be at what j comma s level to split, such that some notion of q1, let's say, plus q2 is small. Okay. So what is q1 and q2? Just like in the regression case, I had squared loss on the first region and square loss on the second region, right? So I'm just writing it as q1 and q2 because if you see here, I've used q function as a node impurity function, which just happens to be the same thing. So it's just some number minus all y's of all the points that belong to that region. Okay, so that was the case for regression. I just wrote q1 and q2, and I'm gonna give you a few options for q1 and q2 that you've seen. So the first option is called just the misclassification loss. The misclassification loss is going to be 1 minus p hat m, and I'm going to put k km. Okay, so what is km? Think of km being the highest, the index corresponding to the highest number of class points. So okay, so for example, in my 3 class example, right, I had p hat m1, p hat m2, and p hat m3, right? So there are 3 numbers in my 3 class example. So for example, I said if I had 10 points, let's say p hat m1 is 0.2, this was 0.3, and this was 0.5. So then k of m is just 3. Okay, I'm just picking the index of the highest occurring classes, highest occurring class in that region. Okay, it's just basically saying how many points did I misclassify, because the majority class in that region happens to be class 3. Okay, and so this is a loss that was that's there. That you can define for any region, and therefore R1 and R2 as well. So you are saying if I split the region R0 into 2 parts, for each part I can ask what is the misclassification loss, right? As a dependent on my choice of j and s, and then I'm going to pick the j and s that corresponds to the smallest misclassification loss, sum of the misclassification losses. We just change the squared loss to misclassification loss for each new regions that we form. Okay, the 2 parts that we formed. Any question? Yeah.
So C1 here would be only like a particular class that we select in that region.
Yeah, I've not used the notation C1 here. So the equivalent thing in classification trees is going to be this PM case. So P case, for example. So in the regression case, for each region I had 1 number, the C, which was like the average of the y's. In the classification case, I have if let's say 3 classes, then I have 3 numbers.
Maximum probability class.
It's just the 3 numbers. Each number corresponds to what is the proportion of that class in that region. Okay. So if there are 3 classes, there will be 3 numbers. Like in this example, I said if I have 10 points, 2 happen to be blue, 3 happen to be green, and 5 happen to be red. Then these are the proportions of the 3 classes. And then all I'm saying is the misclassification would be ideally in a region if one of the classes occurrence is higher, then you would ideally say that that is your class in that region. And so misclassification is saying that what is the 1 minus that proportion, because that 1 minus that proportion would be your roughly errors. Okay. And the second one is called the Gini Index. I don't know where the name comes from, but it's just a function of, it's not a function of the best class there, so it's not a function of km, it's just a function of these three numbers. Okay, it's just going to be sum over little k is equal to 1 to capital K of p hat mk times 1 minus p hat mk. So let's say I picked a j and I picked a threshold, and I got three numbers for the new region R1, then I can compute this number for that region R1. Similarly, I can get the same computation, different number for region R2. I can add them up and get the new total score for breaking the original region R0 into two parts. Okay, same thing. So we're just changing from square loss to misclassification loss, Gini index, and so on, because we are not in the classification setting. Okay. Square loss doesn't make much sense in a classification setting. Yeah, p hat mk is just this. I just defined it. Yeah, even this one, misclassification, I could have written it as max over p hat mk, okay, because that's what it is. But I just wrote it as, in the book they use km as a notation. But yeah, for in each region you'll have a bunch of these p hat guys, okay, and these scores that you associate with each region happens to be just functions of them, okay.
So what is the Gini index? Like misclassification is included.
Yeah.
What is
It's a there's a couple of interpretations. One is it's some notion of variance. How much of variance is there in that region? So in the sense of, think of a region M. So we have already indexed it as M. M represents a region M. In that region, it happens to be, let's say there are three classes. There are three different numbers: 0.2, 0.3, and 0.5. It's saying that because there are three different numbers, I'm going to compute some notion of variance for this region. So I don't know if you remember from some previous class that the variance of a Bernoulli random variable is p times 1 minus p. Okay, if you flip a coin with bias p is a parameter, then the variance of that coin is p times 1 minus p. Okay, so you can see that something similar is happening here. So we are doing p times 1 minus p and summing over all k classes here. So it's basically saying that if you have a very highly biased coin, so either then you'll have essentially a low score, okay, because a highly biased coin will have less variance. Okay, so p times 1 minus p is very high if bias is 0.5. Okay, and p times 1 minus p is very low when p is either very 0.1 or 0.9, let's say. So the intuition here is just it's some score of how good that region is. So all these are supposed to be scores, one number that you attach to how nice that region is. And nice, by nice I just mean that ideally you would want a region to capture, region to have all points which are the same class. Okay. Ideally you want to get that, right? I mean, that would be the best. Let's say you had two-dimensional data and you had bunch of points, oranges on one side of some threshold and blues on one side of the threshold. Then picking that threshold would give you oranges on one side and blues on one side perfectly, and then that would be the best case scenario. That would be your best classifier, right? I mean, best region partitioning of your input space. So that's what we want to achieve, and so these are scores for when you are not able to do so. Okay, when you have a mixed you have various different classes, points of different classes also in the same region, you're assigning a score like this. Okay. Any other question? Yeah.
Maybe again, so in the Gini, you take the PMX is in each leaf the like the majority class, and then the summation is over different leaves, or it's in one leaf, the same leaf?
Don't worry about the leaf part. So we are just asking about. So before you understand what leaves and non-leaves and so on, all I'm saying is you have a region, okay, which means there is a node. It could be the leaf node currently, or it could be an internal node. But ideally you want to split leaf nodes only because you've already split the internal nodes. That's true. At a node, all I'm asking is I want to split it into two parts, right? That's the idea for tree construction. But for every region, I'll have k numbers. In this case, in this example, I have 3 numbers. Okay. Every region has 3 numbers. Instead of in the regression setting, I had 1 number. Here I have 3 numbers. Okay. Which means that so those 3 numbers just correspond to the proportion of classes in that region. Okay. If I have 10 points, 3 are blues, 2 are oranges, and 5 are reds, then these are the proportions: 0.2, 0.3, and 0.5. Okay. Those 3 numbers for that region. Given these 3 numbers, I can compute a score for that region. How good is that region? Okay, that is the score. Okay, one of these scores. Let me not use even use km here. Let me just write it as 1 minus max over k is equal to 1 to capital K of p hat mk. So these are all just functions of those 3 numbers. Okay, it's just functions of those 3 numbers. And those 3 numbers, ideally, you want those 3 numbers to be very skewed. In the sense, one of those numbers has to be very close to 1, and all the other numbers are close to 0. For example, you can think of it this, right? If one of the numbers was close to 1 and all the other numbers are close to 0, then misclassification loss is 0. Right? Because one of the numbers, max over those numbers, will be one of that number will be very high, and so 1 minus that number will be very close to 0. Similarly here, if one of those numbers is going to be very close to 1, then that means that all the other numbers are close to 0, and for each of those terms, the numbers which are close to 0, each of this product is also close to 0, and for the term where that number is high, this product is again close to 0. Okay. It's just, maybe there's actually a picture of this somewhere. Okay, let's see. Yeah. So this picture is trying to kind of get an intuition for what these scores mean. The scores are just saying that, let's think of just 2 classes, okay? I was giving an example with 3 classes, just think of 2 classes. And think of this P as the P hat M1, okay? Forget about, because P hat M2 is going to be just 1 minus P hat M1, because the total sum should be 1, right? So it's just saying that if P hat M1 is, there's 50-50 percentage of both classes in your region, that region is really not a good region. And so this, on the y-axis, is actually the score itself. It's 0.5, actually, I guess a scale version of the score, I'm not sure, but it's 0.5, and when that P hat M1 is close to 0 or close to 1, then you have very low score, because you know that either it's of class 2, most of the points in that region are class 2 or class 1. Okay. Similarly, Gini is very similar in intuition, in terms of, it's also trying to compute a node impurity score, actually. If you have a mixture of multiple classes, you're doing somewhat bad recursive partitioning of your node. Okay. Okay, so and you can use, okay, I guess there was one more function. Oh, okay, there's another thing which you already seen, which is called cross entropy, also called deviance. But cross entropy, I guess, loss or score is just negative sum of k is equal to 1 to k of p hat mk times log of p hat mk. Okay. Actually, this you must have seen in multi-class classification, because cross entropy loss is something we came across there as well. Okay. So all these 3 functions are very similar. So yeah.
Is that log base 2?
Uh,
So remember in the errors data mining class, I think she had taught it as log base 2 to calculate cross entropy. That thought there's a different log.
it doesn't matter, right? I mean, you know that log to the base anything is fine. I mean, you will get a different scaling. You know, it's just a constant scaling that you'll get. So I don't know if you know this. I mean, I'm trying to recall. So log of a to the base b is log of a to the base c divided by log of b to the base c or something. So if you want to change b to 2 or e or whatever, then you'll just get another constant, scaling constant there. Okay, and so in the so that's pretty much classification and regression tree. So the most important thing, I mean, mostly you'll probably use some packages, but you need to understand what's happening. You know, why certain nodes are coming up in your tree. You know, you plot a tree, it looks, you know, you see the tree, but you need to understand what's happening in each region, how the regions are splitting. Okay. So there are some issues with tree-based classifiers or tree-based regression models, and I'm just going to list a few issues. The first thing is categorical variables. Okay, which we really, yeah.
One thing about the trees and
Yeah.
is there any indication on when we would expect each of them to work best? Or is
Each of these choices?
yeah.
No, I don't know. In the sense, all of these are intuitively trying to capture some notion of impurity, and it's just a design choice, I would say. It's not clear at this point which one is a good choice. Just like the choice of loss function, whether it's square loss or absolute value loss, or and we will see some other loss functions later on in this lecture. Which one you choose is just dependent on some considerations. For example, you may want loss to be highly sensitive to extreme values. Okay, so for example, here if p hat happens to be 0.2, you're penalizing it to be, you're giving a higher loss value. So you're not happy with, so you really want p hats to be either very close to zeros or very close to 1. Okay, so that's the intuition. So you're penalizing more. That would be the intuition for choosing a loss. Okay, like entropy penalizes, I guess it's written entropy here, but it's cross entropy for higher dimension. When you have more classes. So you're penalizing more if your p values are not 1 or 0. So you only when they're 1 or 0 you have 0 value for the loss, and if it's slightly away from 1 or slightly away from 0, you're penalizing more with Gini and entropy compared to misclassification. That's it. Otherwise I don't know of other reasons. Okay, so actually let's take a break for 5 minutes and get back.
I understand that you're trying to represent C and you're trying
This
to
is just one
represent
number.
with C. But what is it visually?
Visually, actually last class I showed it, which is this. This is just this. So visually, this is what's happening. You have to approximate some function.
Mm-hmm.
So this function for regression is the conditional expectation of y given x is equal to x. Remember, for linear models we were saying conditional expectation of y given x is equal to x is linear.
Yes.
Right? Here we are approximating that function using these constant region function. Okay,
so
where in each region there's a constant number.
would you say that for a 3-dimensional space it's a plane which is 2-dimensional, and for a 2-dimensional
No, it's not
space,
even for 2-dimensional space it's not a plane, right? It's like constant.
as in
But
it
even-
becomes very like 1-dimensionless, something like that.
No, it doesn't become 1-dimensional. It's like a very messy function, right? So if you think of linear function, it will be like a plane. That's linear model.
These are multiple planes.
These are multiple flat flat regions.
Okay.
Yeah, these are multiple planes, but it's
Multiple
a combination of them, right? So
Yes.
it's the total sum is not going to be any plane.
Yeah,
or anything.
ultimately it cannot be two-dimensional because the region itself is three-dimensional. I understand that. But
No,
I'm
here
trying
region is
to-
2-dimension. Here the region is x1 and x2, and f of x. So the f of x, see this f of x is being plotted here. So we we still have the 2-dimensional example that I was talking about.
Okay.
But so think of this actually. Where is this? So think of this region. Okay, this is the x1 x2 plane, just like that. Think of region 1. In region 1 corresponds to this place here. For the region 1, there's a constant c1. Okay.
Okay.
That's being plotted on the y-axis.
Okay.
And similarly, in the, let's say in this thin strip region here, there's another constant here. This is a constant.
But why is it in?
Why is it one, not one number?
I
But
can still see it in a three-dimensional space.
this is 3 dimensions because the 2 dimension is the feature space and the 3rd dimension is the function.
Oh, okay.
Always your function is going to be one additional dimension than the
Yes,
input space,
okay.
right?
Okay.
So these are the constants, and you cannot think of them as just hyperplanes. These are combinations of levels actually.
That is what you meant by special hyperplanes.
No,
You
special
said-
hyperplanes
you
just
mentioned
means
something.
I mentioned that special just means whenever I split a region, I'm using just the vertical. I'm coordinate aligned
Yes.
cuts. They are just special hyperplanes, right? In general, hyperplanes can be arbitrary.
Yes,
I'm just
they are.
taking parallel to x or parallel to y.
Oh, okay.
That's why I said special.
Okay.
Those are hyperplanes. But these f of x itself is a very complicated function. It's like sums of levels type of thing. Arbitrary levels actually. It doesn't have to be increasing. It can be anything.
Okay.
Okay.
And for binary split, we were splitting them into two regions, and then you're minimizing both of them separately.
If you consider two regions, this is the score that you will assign.
Yes. Why can't you minimize the sum of these both instead?
No. Yeah, you can minimize the sum, but each term is irrelevant, unrelated to the other one,
So you're saying minimize this, and then minimize this, and then minimize the entire thing as well?
and add them. That's it. No, minimizing the entire thing is the same as minimizing both terms separately,
Okay.
because minimizing over C1 doesn't appear here, which means
Yeah.
that this has nothing to do with this.
Yeah. They're mutually not.
Yeah, they're unrelated optimization problems.
And during pruning, you merge two nodes, right? And that
Yeah.
is for binary split and trees. What if this tree has more than binary split?
No, you can merge multiple ones as well.
How do we choose which ones? As in, can we merge subset of those multiple nodes?
So merging is still merging is a choice. So you want to ask whether you want to merge these leaves into. So basically, merging is the
say I
inverse
have-
process.
Yeah, I have three splits instead of binary.
Yeah, you can have 3.
In those three,
Yeah.
am I supposed to merge all three of them, or can I merge any two only instead? Like again, it is all
You
coming
can.
back
That's
to my
again
criteria. how I
your
want
choice.
to-
It's again your choice whether you want to merge all 3 or 2. But ideally, people have only been working on with binary trees.
Okay.
So you have to merge. You have to merge means at least you need to have 2 parts. So binary trees exactly has 2 parts, so you merge.
Yeah,
but
I'm
with
going
3,
to do a single
you
piece.
could merge a subset of them. But the 3 or more, you can merge a subset of them, and then the tree structure becomes messy. It's not going to be regular. Okay.
And
So it's not considered. If you are asking in practice, it's not considered. The
yeah,
variation that you're asking.
after I asked you, I just realized it doesn't even make sense because my motive is to prune and go back to previous level.
Yeah, but you can merge and you still you retain the number of nodes. You don't
the
take these.
node. I mean, the level remains the same.
No, but you
also.
could merge, right? I mean, merging is your choice. If you think it's a better performing function, prediction function, you can merge.
And I am still unclear about what PMK is. Exactly.
It's just a number. Just like in regression, you have one
PM is
number.
the region.
M is the region.
Okay.
Uh, K is the kth class. You're just
in a
asking
region-
for each class how many points are relative number of points in that region. So fix the region M. Okay, M is fixed. Now you're just asking how many of class 1 are there, how many of class 2 are there, how many of class 3 are there.
Okay, so this is one region, and in this there are 3 classes.
Yeah, let's say 3 classes. Yeah,
Something.
potentially 3 classes.
Okay, so this is
I'm just
PM1,
asking.
PM2, PM3.
Yeah, but divided by the total number. So P happen to be not just the counts divided by total number in that region.
Oh, got it. Okay.
Okay.
Thank you.
Yeah.
Hey, so I just had a question about one of these sample exam questions,
Yeah.
just to make sure I interpret the question correctly.
Yeah.
So in what situations would sampling be useful? Are you talking about sampling in general, like in order to just try to estimate the distribution of something, or just to use for
Yeah, or the
testing?
mean or the variance. I'm just asking
Okay.
in the context of Gibbs sampling. there was a small section on Gibbs sampling, right?
So is this specifically about Gibbs sampling or all kinds of sampling? Because I wasn't sure.
Just Gibbs, whatever was introduced. There was a motivation for why you would want to do sampling, right? Which was that sometimes it's difficult to compute functions of arbitrary distributions.
Okay.
Like even expectation of a bimodal Gaussian, it's not. I mean, it's I guess bimodal Gaussian it's easy, but if you had multi-dimensional Gaussian, sometimes computing expectation itself is hard. Mm-hmm. So you want to just sample points and just take the empirical average. So that's why sampling is useful.
But this question expands beyond just Gibbs sampling, right? It's just talking about.
No, you can just so whatever is introduced in the class. So so you can just say why would Gibbs sampling be useful?
Right.
Is enough. I'm not asking outside. You may have other reasons. You can state them as well. It's fine.
Okay. So just based off the lecture.
Yeah.
Okay. Thanks.
So I wanted to talk about the project thing, how to go about it. So I'm Tanvi, and I had maybe about the project recognizing characters. So you said we can make our own data set.
Yeah, you can.
So I wanted to know how do we make that with the own handwriting and how do we project it?
You can write it and take a snapshot, right? I mean, you'll get a very high resolution image. You'll just have to scale it down.
Okay.
So the existing handwriting data set has 32 cross 32 or 16 cross 16 small images.
Yeah.
You will have to do that for some, maybe.
So I was wondering if UIC has such, tools or, lab wherein I could, simply, like you have this board wherein you're just typing things and it recognizes the image, right?
Okay.
So is there any such thing that could make the task easy? Because I would definitely look forward to a bigger data set, at least 1,000 images,
Yeah.
So it would take a lot of time to scaling.
I'm not aware of UIC resources at this point.
Okay.
Maybe drop a question to TAs. Maybe they know something because they've been here. So generating data stuff and it'll take a long time. So if you don't want to go that route, that's fine. I just suggested that as an example.
That was the key thing
in your proposal.
Yeah. Because that was the good factor.
So I would say with existing for the existing data set anyway build your script and then you just have to change the data set with your data set, right?
Yeah.
So that part you can simultaneously try to see what's the best way to be efficient and still get that data. Okay. Yeah, you don't have to just focus on just numbers, for example. You can focus on other things of your own of your own writing. Yeah. I'm not sure, but let me think about it. Yeah.
Okay, thank you so much.
So these are all going to be assignments right.
Okay, so let's resume. So I was talking about some issues with trees. I'm sure you must have seen other practical issues with using classification regression trees. So let's look at it from more conceptual viewpoint. What are the issues with using tree models? Okay. So I've listed a few issues in the notes, and I'm just gonna briefly just mention them. The first issue is with categorical variables. So in this whole discussion that I had in the morning, I really didn't talk about whether the input variables were numerical, categorical, or ordinal. So if the input variables happen to be categorical, then let's say it's categorical variable with q levels, q values. Then basically there is no split like this, right? What is xj less than equal to or greater than equal to some s mean? Okay, this is not clear. So with q categorical values, so let's say one of your input variable is cat, dog, and fox. Okay. Then there are three values. So okay, this notation. Okay, what does So the split happens at a number, right? So it's not clear what this means. So for example, if you have a cat, a dog, and a fox, maybe you can split it this way: cat on one side and dog and fox on the other side. You can split cat and dog on this side and fox on this side, right? Or you can do the other way, which is this one in one set and this two on one set, right? So there's so many split choices, and so in general, so there's 2 to the power q minus 1 choices. Okay. So q here is 3. So 2 square minus 1. So there are 3 choices of splitting. Okay. So this is how you try to split categorical variables. It just becomes too unwieldy when q is let's say 10. There's just too many choices. Okay. Too many split choices, right? So how do you address this? There are some heuristics to address this. You might have seen them in the data mining class, or you can refer to the book. But in general, this is an issue. This is a principled issue, and there are some heuristic ways to address this. But in general, there is no principled way to kind of deal with this. Okay. Yeah. Where is it? Where is it saying binary? Binary splits. Yeah, binary splits. Yeah, so that's also another good question, which is the issue of why binary splits. Again, this is a choice that we made. So whenever you build define a prediction function, you make tons of choices. So this is one of the choices. It just turns out to be a good enough choice. Okay, you can do ternary splits, you can do 4 splits, and so on. It just turns out to be good in practice. So there is no other reason. Okay. And also there is another question. Why xj equal to s is the split? Why should I split R0 into R1 and R2 with just xj is equal to s for some j and s, right? So why can't I do sum over aj xj, j is equal to 1 to p is equal to s as the split? Why not? Right? I was just taking a split which was exactly on one coordinate, take the left side or the right side as 2 regions, right? But why not some convex combination, some, I guess, linear combination? I guess this is a sum of the values, them being greater than something and less than something, then I can split. Okay. So all I'm saying is here, so this is a special case, right? Here all the aj's are 0 except for the jth one, it's 1. Okay, then this is a special case of the first line is I guess second line is a special case of the third line, right? The question is, why not use this type of this type of a split choice? So whenever a sum of these xj's is equal to or greater than s, then I consider that as one region, and when it is less than s, I consider that as another region. Okay, these are all things to think about. I mean, you will see that these are all probably bad choices. Because this just makes it complicated, right? I mean, you can kind of intuitively think that if I'm considering arbitrary combinations of xj's, where I have not even specified what aj's are, then it just increases the number of choices I need to make. When I had to only pick a coordinate and pick a split point, I had very less number of choices, right? I only had p variables for the first coordinate, for the j choice for the j, and s was every, let's say, interval or something. So some resolution I could have chosen. Here now I have to consider all sorts of combinations, so it's not clear. It just increases the number of possibilities. So it just and also it becomes a bit messy. It doesn't leave interpretability. You will not get rectangular regions. Okay, that's, I guess, a more fundamental thing I should have said. You will not get rectangular regions here, depending on the choice of A. But not getting rectangular, yeah. Rectangular may be bad. because it has too many degrees of freedom, right? Here there is no. So if you want to pick a split, so you basically, my question is how to go from R0 to R1, R2, two regions, right? Which their union is the original region. Using this gives you very less choices, but it will only give you rectangular regions, right? Rectangular cuts of the original region, vertical or horizontal cuts, for example, two-dimensional case. This one will give you arbitrary oriented cuts, okay, which may be desirable because it may better capture some pattern in the data. But then you have too many choices, like what AJs to pick and S. So that's like a P+1 dimensional optimization, right?
So it's just hard, like computationally expensive.
Computationally,
Okay, we can
yeah.
do it.
So there is a pro. So as you said, using this may capture better patterns on the data. For example, why would data be exactly aligned with this coordinate axis, right? Why should you split exactly on that? So that's why this may be useful. But then computing it is computationally hard, computationally difficult, and they don't see benefit in practice. So people don't use it. But you can try. I mean, you can write your code and use these. It's fine. I mean, you should be confident that you can use this. You know, these algorithms are not complicated. You don't have to use an existing package as such. And the fourth thing is sometimes, you know, so there's a lot of sensitivity to initial split choices. So from the root, which variable you chose to split kind of completely determines how you're going to split the remaining regions, right? So there's a lot of importance to the first few split choices, okay? And if you go wrong there, wrong just means that you could have done something else later on, but you made a wrong split, you know, suboptimal split there. It doesn't capture the actual pattern in the data. Then you're already kind of away from the best regression function, you know, that you're building, okay? Regression model that you're building. These are just intuitive points, okay? And also fifth one is if expectation of, let's say in the regression case, expectation of y given x is equal to x is smooth, then you're splitting your tree representation, yeah?
For the point number 4 where it says like sensitivity to initial split choices,
Yeah.
like does it not depend on like very fixed variables like suppose information gain or entropy, just in case?
Yeah. So you will make the splits based on the stuff that we just talked about, entropy, Gini index in case of regression.
Yeah,
In case of classification.
If we have like 5 variables and if we just calculate the information gain and entropy of all those 5 variables, is it like not a very obvious choice where we can actually look at those parameters and determine that this is the only root code which is feasible?
See, I think you're thinking in terms of the cost or the score function. I don't know what information gain is. I didn't describe it in this class, but I just gave you a few options, right? Square loss for regression, and I said Gini index, cross entropy, and so on for the other one. So those are the scores, and based on the scores, you will split appropriately. That's fine. But the whole procedure is greedy. You're doing stage-wise. You remember at the beginning of the class, I said ideally you would want to find all the regions and all the constants in these regions at the same time. That's the ideal situation. It's just that problem is computationally difficult, and so you're doing it in a greedy manner, which just means that if you're doing it in a greedy manner, you are first of all being suboptimal. Okay, the optimal solution when you find the m optimal regions simultaneously, that solution is going to be better than greedily finding one region at a time. You know, splitting regions. Okay, and therefore, since you're doing it greedily, you could be off. You're already being suboptimal, and you could be off because of the choice of initial splits. Okay, the choice of initial splits according to Gini index or entropy or whatever is fine. That is not the issue. Okay. So the issue is already that you are being suboptimal, and so in a suboptimal greedy sequential procedure, you may make a wrong step at the beginning of the wrong step is not wrong because of incorrectly computing a score. It's just the wrong step is because you're already being suboptimal, and so you may be veered off in a direction which is very far away from the optimal one. Okay. The optimal one was to do all the regions simultaneously. Okay. feature selection. I don't know what that means.
So when we actually do pruning, so what we are doing is we are just nullifying all the variables which has like very less significance in our model.
No. Here pruning just means collapsing vertices, like basically the inverse of splitting regions. We just merge regions in this narrative that we have had in the first part of this lecture. We are not removing coordinates. We are not removing input variables here. Okay, that can be something that you can do on top of all this, but that's not what this. That's not what I have described. Maybe we can discuss again after the lecture. Any questions? Are there any questions exactly related to what he was asking, or? Okay. Yeah. I'm just saying sensitivity to initial split choices. Okay. And the fifth issue is if the actual regression function. So this is the ideal regression function if you knew the joint distribution, right? You've seen this in the midterm also. If this is actually smooth, we are saying we are going to partition our input space into regions and then put a constant value there. So it's like it's like a jagged function, right? It's like suddenly changing from some level to another level at the boundary of your region, for example, boundary of two regions. So that can introduce some issues, right? Ideally, the truth is smooth, but then you're having like a jagged surface, right? So that could be an issue. Okay, so let's look at another quick consideration, which is missing data. Okay, which one? Yeah, if you have a continuous function, if you remember, actually there's a picture here, right? So think of this two-dimensional example. So x and y is the input space. So okay, x1 and x2 are the input space, and in this case, it happened to be this was the tree. Okay, and for each region of the tree, you have a constant value. So there is maybe 0 here, 1 here, 3 here, 3.5, and let's say 4, some numbers, right? But in reality, the conditional expectation of y given x1 and x2 may be a smooth function, like a plane, for example. Okay, which means that the jump from this part of the region to that part of the region close to the region boundaries is gonna, is not a good approximation for that smooth function, right? You're jumping and you have a smooth variation. Okay. So one way to fix this could be to have really, really, really small regions, right? Really small regions. Then it's like, I don't know if you've taken a class in calculus. They talk about integration using, I guess, what is it called? Integration using, like if they show one-dimensional integration, they talk about rectangles, and then the width of the rectangles kind of captures how much error you have in the integration, right? So it's something like that here. Okay, so there's a small note on missing data. I'm going to skip that because let's. One thing you just need to know is a couple of phrases there, which are kind of key assumptions that you will have to assume while going ahead with data processing. One is the first phrase is called missing at random. Okay, missing at random just means that observation entries that are missing in your training data, like it could be one of the features has a missing number in your training data. It could be missing at random just means that it doesn't depend on the observations that you made. It doesn't depend on the observed data. Okay, the missing data doesn't depend on the observed data. Sorry, actually, let me state it correctly. So there are two notions to formally talk about missing data. Okay, So let's say our observation is actually let's say z is y and x, okay, and z observed is y and x observed, okay, and x observed just is a as a subset of x. So think of x as a your p-dimensional input variable, okay. Maybe you're missing some observations in that p-dimensional input variable, okay. Actually, okay, let me just write this, make it very clear. So let's say you have an X matrix which is n rows and p columns. You just have some missing numbers in there, okay. Some numbers you don't know and you didn't collect or you couldn't measure, okay. Let's call X observed the things which you have collected, okay. And then the remaining ones are missing, and so we call data missing at random if the probability of let me call it missing. So I don't want to introduce another notation, but probability of missing given your data, all data, just depends on probability of missing given z observed. Okay, some parameter. So all it's saying is the missing data only depends on, so the missing data doesn't depend on what the missing values themselves were, okay. So you didn't miss the data because you observed the data and therefore you didn't copy the, you didn't make the measurement, okay. So that's all it means. All it's saying is, the reason why an entry is missing is not because I measured that number and I kind of forgot to capture it. That's all. It's basically like saying I had a very high value, so I kind of deleted that. You should not do that. Okay, that's what missing at random means. But it can depend on observed values. For example, I'm making measurements of temperature. Okay. Maybe I measured a very high temperature, and because I measured that, I am not copying it into my observation. That's the bad case here. But you missing a temperature value because you observed other temperatures is fine. Yeah.
Just to be clear, you're saying that the reason data could be missing doesn't have anything to do with
the missing values themselves. It can have everything to do with the observed values, but it should not have anything to do with the missing value itself.
Okay.
Like, so I wrote it loosely here. The left hand side of this argument, probability of missing. All I'm saying is, so think of this as a random variable R, where, for example, ij represents whether the ith observation's jth value is missing or not. Okay. So this is a random variable which is saying the ith observation's jth value is missing. The probability of that missing has nothing to do with any of the missing data. Should not depend on any of the missing data. Okay. It could depend on observed data. It need not depend on observed data, but whatever. It should not depend on you seeing something and then deleting it. Okay.
So we're assuming that it can be so let's say that you have a row and one value is empty.
Yeah.
And we're saying that it should be independent in the column, but it doesn't have to be independent in the row. Is that?
No, it's just saying that. So that's not interpretation. All I'm saying is, one example of when this makes sense is, let's say you have observed everything, and then somebody comes up and keeps flipping coin and deletes some observations. That is called missing at random. Okay. You flip a coin. If it's heads, then you delete that number in that matrix. If it's tails, you don't delete it. then that has nothing to do with the values of those locations themselves. Then that is this case, missing at random. Okay. But if you look at the values, okay, this value is too high, this value is too low, therefore I'm deleting it. That would be not missing at random. That would be a bad case. That would be basically biased data. Okay. That will lead. So basically, if you have biased data, you'll lead to wrong, incorrect conclusions potentially. Okay. And so even in this situation is not good enough for us. Actually, what we want is missing completely at random, which just means that the probability of missing given the whole data should be just the probability of missing. In a sense, the probability of missing should not even depend on what I have observed. Okay. So I guess this is more intuitive. This is the one. So the coin tossing and deleting entries example. The coin tossing had nothing to do with what other entries were there in that matrix, right? So that would be this missing completely at random. So the entries are missing because of completely some exogenous reasons, and not because of what I have observed, and definitely not because of the entries that I want that got deleted. Okay. So in this case is where you would imputation makes sense, for example. So missing at random needs some other more complicated treatment, so we are not going to look at that. But all I'm saying is, when you got a data set, you have missing entries. If you impute it, you are implicitly saying that I'm going to assume that my missing data is missing completely at random. Okay. So if you're going to impute it, then this is what you're assuming. This assumption can be correct or incorrect depending on how the data was generated or collected, right? That's all. That's what this conditional. This is the only difference, right? So it's left hand side is the same, probability of missing given the whole data. The first one is saying is a little bit of a less. So this is a strong condition. So this is missing completely at random is a more stronger criteria than missing at random. Missing at random is just saying probability of missing given data is just it doesn't depend on the values of the data that were missing. Okay, which means that it just depends on. It could depend on the data that you have observed, Z observed. Okay, here we are saying that it has nothing to do with whatever data you observed or not observed. Okay, that's all. That's what I gave you an example, right? If you flip a coin and delete entries of your matrix, then that would be missing completely at random. That would be this case, because the probability of an ijth entry of your matrix X, capital X matrix missing has nothing to do with any of the entries in that matrix. That is missing completely at random. Do you understand? Like the other one is more complicated. So where it's complicated in the sense that you just want to kind of decide. So let's say the other one could be looking at, let's say you had a matrix and let's say it's a five columns. You kind of observe the first two columns and then create the bias of the coin flipping, create the bias of the coin and then delete the entries of the next three columns with that bias. All I'm saying is that the coin flip bias can be dependent on entries of your matrix. That is an example of. See, all I'm trying to say is I just constructed an example where I'm saying it can depend on some entries that you want to keep in your data. Okay. For example, you can make the coin bias, a function of the first entry of your data and then delete everything else based on that bias. That means that therefore the missing depends on the entry that you kind of kept frozen, which it's a bit contrived example, but that's what it means. So this is a special case of the previous one. So the example that I gave applies to both. It's just that you are asking for an example which only applies to the first one and not the second one, right?
So an example could it be like we have age and name,
yeah,
and some names are missing, and we have observed that like only for females the names are missing, and so there is a relation, and that would be the first case. right? And in the second case would be names that are missing regardless
Random.
of the gender.
Yeah, yeah.
Is that-
So in the first case, names are missing, but they're missing because of male-female entry, which is not missing at all. Yeah. If so, depending. So if the model is like that, yeah, then that's missing at random. Yeah. 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 It's a good. Yeah. Yeah, which is the first case. Yeah. Yeah, that was a good example. Okay. Okay, the reason why I brought this up is because with missing data, you can actually deal with missing data a little bit easily with tree-based methods. Because if data is missing, then because your tree is based on splits, right? Where does the data point go? For example, for prediction, you just want to see where the data point goes. Okay. If for example your new observation has one missing entry, okay, and it happens to be at the split point where that entry is supposed to be compared, then you are at an issue, right? I mean, you will have an issue. But there's a way to kind of change the tree construction process so that you don't get stuck. Okay, I'm not going to describe that because I want to go to talk about boosting. Actually, not just Adaboost, but another interesting boosting method called gradient boosting, which probably is not seen. So I want to get to that. So I'm going to skip the issue with missingness and tree methods for now. Okay, we'll get back to it if there is time. So have you come across Adaboosting in the other class? So Adaboost, I guess. Yeah. Okay. So just remember, why are we talking about tree methods, Adaboost, and what else are we talking about today? Random forest. These are all more flexible models than the linear models that we have seen in the first 5 lectures. Okay, that's the whole point of this. Looking at all these assortment of methods. Okay, they're more flexible than linear models, so can capture more patterns in your data. So okay, let's look at Adaboost. Okay, so Adaboost is this technique where it combines many weak classifiers. So okay, and leads to good prediction performance. Okay, so the keywords are weak classifiers. So this is just a loosely used term. Weak classifier just means that the performance of that classifier. Let's think of a 2-class classification problem. The performance of that classifier is, let's say, 60%. Okay, 60% misclassification. 60% classification rate or 40% misclassification rate. It's very close to being random. Okay. So let's look at just the 2-class setup, which is where Adaboost M1, just the naming convention by the original authors, is used. And so what does the classifier itself look like? Just like in the tree-based method, I said the classifier itself is supposed to be. So this is, first of all, I'm talking about classification setting. I think for regression also you can do something similar. It's not called Adaboost.m1. Okay. So just like in the in the tree setting, I'm gonna just write down a classifier. So g of x is a classifier. Instead of f hat of x, I'm gonna use g of x. Okay. Is going to be just the sign of sum over m is equal to 1 to capital M of alpha m g m of x. Okay. So this is the general classifier that I want to focus on. So just like in the previous case, I had regions and constants in the regions for the regression tree. Similarly here, this classifier has a bunch of things going on. One is these coefficients in this sum. So there are m terms in the sum. These coefficients are the parameters of this classifier. These are called weak classifiers. Okay. And so weak classifiers and their coefficients together define the Adaboost classifier. Okay. So I mean, I have to further describe what the weak classifier parameters are, but given the weak classifiers and the coefficients, this completely determines the Adaboost classifier. And so the Adaboost classifier is just I would say a sum of bunch of classifiers, like an ensemble, or I don't know what you call it, collection of, it's just a weighted sum of bunch of classifiers. And then since it's a two-class setup, they're just taking the sign. Sign just means whether the sum is positive or negative. And if it's positive, you output the class to be 1. If it's negative, output the class to be -1. So the classes themselves, so the G, okay, I've been using G, belong to a -1 and 1, let's say. There's a little bit of abuse of notation. I'm also using G as the function itself, but they have used that notation. So. And the key trick in Adaboost, okay, first of all, why is it called Adaboost? Why is it called boosting? So we'll kind of come across it in the next 2 minutes. Let me just so what is the key idea, and then I'll write the algorithm to get to learn these parameters. So it's a very non-intuitive way. So this is the first example where we are talking about, I guess this is the second example. Even tree construction was not directly thinking about a loss function and a model directly, right? So we didn't write explicitly. I think we wrote, although in the tree construction we wrote minimize over the parameters of the tree model, which is region R1 to Rm and coefficients C1 to Cm of the loss of yi, comma the function, right? So here also, for example, all I'm saying is you minimize over Gm, so G1 to Gm to G capital M, alpha 1 to alpha capital M of loss of yi, comma G of xi. Okay, you can do the sum over I is equal to 1 to n. Okay. So this would be the optimization, this would be the search for the best weak classifiers and these coefficients, right? This would be the nominal problem. But just like in the tree method, although you want to do this, you'll do this in a sequential way, in an iterative way. So there is a sequential procedure. At the end of the sequential procedure, you will get a G. Okay, you'll get this a candidate G. Okay. In the tree procedure, in the tree methods as well, you had some optimization problem, but instead of solving that optimization problem simultaneously or directly, you had a greedy iterative procedure for picking regions, splitting the regions, and so on. Ultimately, you got a tree. Okay. Okay, and so let me write the key idea. Is to boost the examples, or basically observations, where previous classifier did badly. So think of, let's say somehow let's think of not from the beginning. Let's say we have Gm minus 1. Okay. Okay, let me call it. Let's say we have Gm, which is a classifier that we have somehow included in our sequence of classifiers, weak classifiers, and I want to get Gm plus 1. Okay, that's the next one that I want to add to my list of the sum. I want to add to the sum. So to go from this to this, one key step, which is going to be so these weak classifiers have to be learned from data, right? I mean, all classifiers, you're building a classifier, it has to be a function of the data. And the key idea in boosting is Adaboost is to kind of put more weight on those observations in your data where the previous classifier made mistakes. Okay, that's the key idea. And so the algorithm itself is as follows. So start with so we're going to maintain weights wi. I is from 1 to n. So if there is any inconsistency again with the narrative in the other class, just let me know. So we'll maintain weights on our observations or examples, okay, of our training data. So there are n observations, so I'll have n weights. So initially, let me set the weights wi to be 1 by n, okay. And then for m is equal to 1 to capital M, so I want to have ultimately a sum of mv classifiers, okay. Okay. First thing, fit GM given data and weights. Okay. So this is still a black box at the moment. I'm just saying fit a weight classifier given data and weights. Okay. How can you use weights? For example, you can bring them as, for example, coefficients in your loss function. So, for example, you can do minimize over GM of the sum over Wi L of yi comma GM. Okay, let me just try it again. Minimize over GM of sum of Wi L of yi comma GM of xi. Okay, another bracket is missing, but I is equal to 1 to n. So if you do this type of minimization, you would kind of are capturing the weights, right? It's a weighted loss minimization. Okay. Let's say you fit this, then compute a number which is called which is just the error of this classifier M. So we fit a classifier, so we can compute the error of the classifier based on training data. Okay, I have loosely written here. I'll write down the formulation, but the formula itself is not very critical. Some error, some performance score for this classifier. Okay, I fit a classifier. Given I have the data, I can just compute the error of this classifier. Okay. Yeah, train data and weights. Weights are always tagged along. Okay. And then you set new weights Wi, okay, based on error M. So there's one number that we compute for this classifier, okay, let's say it's 2, okay, some number. You're going to use that number and kind of update the weights of each of your observation. Okay. And the update formula is also not very critical to understand. So what I'm saying is, okay, so what is critical to understand here is that I had an observation I. Let's fix an observation I. Maybe it was incorrectly classified by this classifier GM. Okay. Okay. Then all I want to intuitively do is try to increase the weight of that example because it was incorrectly classified. So I want to next time kind of give more weight to the loss if it happens if the next one is going to incorrectly classify it, so that the next one ideally should not incorrectly classify it. Okay, that's all. So the new weights are just going to be, okay, there was a total error M by this classifier. Okay, that's some number. But if this example was incorrectly classified, I'm going to use that number to kind of scale this number up the next time. Okay. That's how I kind of make it dependent on the performance of the previous classifier. Otherwise, you can just, you don't have to compute this number. You can still say if it was misclassified, just increase the weight on that arbitrarily as well. That's also a choice. But the Adaboost M1 just works this way. Okay. And that's it. So you set the new weights and then you repeat. Okay. And you do this till M steps and you get M classifiers. Okay, and as a side step, okay, I kind of missed it. So you can use error m to also define this alpha m. Okay, alpha m is just a deterministic function of this error m. So you compute this error alpha m, which is the coefficient in your sum of that sum, the functional form that we assumed for our classifier. Where is this? Yeah, this alpha m is just a deterministic function of error m. It's just log of error divided by 1 minus error or something. It's just some simple function. Okay, and at the end you will get g of m is equal to sine of sum over m is equal to 1 to m of alpha m g m of. Okay, so that's the building. Okay, that's the building of this classifier. Just like the tree-based methods, there was some sequence of steps that you were doing to get regions and the let's say coefficients or p hat m case in the classification case. Similarly, you got some classifier like this. Okay. So any questions with yeah?
Would you repeat until you converge to the same weights, WI?
No, we don't converge. We don't focus on convergence at all. We start with some uniform. So these are just saying no observation is relatively more important than the other. So all of them are 1 by n. Okay, initially. So, and then you just you choose a number of guys that you want, number of weak classifiers that you want to include. So this could be 100 or 1,000, and then just keep repeating. This is a for loop.
So that's just that priority, you know, the number of n you want to begin with.
Yeah, the m that you choose, you probably can choose it using cross validation.
Okay.
Yeah. A capital M that you choose.
Okay.
Yeah.
And why do we expect each of these classifiers to be only a weak classifier? Because at the beginning, so the first iteration, I would expect them to be as good as, say, a normal decision tree, right? Because they have
Yeah. So each GM can be a decision tree. Yeah.
So why will they end up being a weak classifier?
They don't have to be weak. I mean, so a strong classifier is also a weak classifier because it will at least perform better than a weak classifier. So we just want some something that can do better than random guessing. Okay, that's all we mean. So if you already have a really good classifier, each G, the first step you already use a decision tree and it's already giving you 99% accuracy or something like that, then maybe it's kind of useless to do more, do these things. Okay. But so this is more less requirement, right? I just want somebody to kind of positively correlate, do better than random guessing. Okay. The moment you have something like that, then you can kind of really boost its performance. Okay. Adaboost, Adab probably means just adaptive boosting. Okay. And there is an explanation of why boosting works. So the way we have described this algorithm, it seems very algorithmic, right? It's not really thinking of some loss function as such. It's like manipulating weights, manipulating weights of the observations and fitting. And even this step I have not completely clarified. How do you fit GM given data and weights? I just wrote the general expression for this. But GM can be a decision tree, can be arbitrary other things. It can be a linear model, for example. Okay. So I have not completely specified step 1. But even without that, there is an explanation. And that takes the explanation of why boosting works, as in why this algorithmic procedure of adding, training weak classifiers on changed data, because data weights are changing, so it's different data sets, right? It's the same observations, but the weights are different. So there is an explanation of why boosting works through the route of, which uses kind of analogy. Additive models. And exponential loss. So let's see. So let's focus on first the additive models business. Okay, we saw generalized additive models last class, right? GAMs, which were just saying instead of a linear, instead of beta transpose x, I'm going to have beta naught plus beta 1 times f of x1 plus beta 2 times f of x2 and so on, f2 of x2 and so on, right? Okay. So I guess it's not directly related to additive models. Let's see. So there is this notion of forward stage-wise additive modeling. Okay. So what does this mean? So this is just another concept that I'm introducing, trying to say that Adaboost resembles the same procedure that this forward stage-wise additive modeling does. And I'm going to describe what each one means, actually, what each kind of word just means. It's quite intuitive. Actually, let me flash that particular algorithm. It's very simple. Okay, so this is the algorithm. Okay, and what is the algorithm saying? It also has m steps, just like Adaboost. Okay, m is equal to 1 to m. I'm saying compute something here. So I'm going to describe what this is. It's saying compute an additive loss. Okay. 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 So in step A, it's saying compute. Okay, let me just initialize some aspect. So in forward stage-wise additive modeling, you are also finding the same thing. You are trying to find sum of m is equal to 1 to capital M of, I guess there's a gamma. Oh, I have this. So we're trying to find beta m times some function bm of x. Okay. So we want to find an f hat of x. Okay. So we are going to assume that we want to find something like this, which is an additive model. So that's where the additive comes. It's the sum of m functions, and each function has a coefficient. Okay, and these are called roughly basis functions because these are just functions that I'm going to add up to kind of construct my prediction function. Okay, and so this is called this is called a general additive model. Okay. I guess in the GAM section, I was just talking about this additive model being just a function of each individual variable, but here I'm saying I'm kind of loosening that assumption a bit, and I'm saying these are called basis functions, and this can be functions of the whole x, whole input variable as well, so the whole vector itself. Okay, forward stage-wise just means I'm going to fit each function bm in turn. Okay, just like Adaboost, and that's where I guess this makes sense, which is that I start from m is equal to 1 to m. I want to have capital M number of functions. Okay, and the first function I'm going to fit is the function which has I need to fit the function as well as its coefficient. I need to know both. So let's say the coefficient is represented by beta, and the function itself is parameterized by parameter gamma. Okay, the two parameters, the function's parameter itself and the coefficient as well. Okay, so I'm going to fit these two quantities in sequence. Okay, just like a greedy way. Okay, I'm going to first so let's say at the beginning of time anyway f0 is 0, so this is not there. So I'm just saying find that function which minimizes the loss between my dependent variable observations yi's and whatever the function itself is predicting, and the function has parameter gamma. So you can, for simplicity, for example, you can think of this as a linear function. b of xi is just xi transpose, I don't want to use beta, but xi transpose gamma, let's say. Gamma is the vector now. Okay. So you fit that function. Okay. You get the coefficients or the parameters of that function and also a coefficient. Okay. You add that function to your, your sum. So that's previous function plus the coefficient times the current function. And then just keep repeating this m times. So basically, forward just means I'm going from m is equal to 1 to 2 to 3 to m. Stepwise just means in each step, or I guess stagewise just means that in each stage I'm just adding one function into my sum, right? So that after m steps I have m functions in my sum, and at each step I'm very greedily fixing everything else and only optimizing the parameters of that function and its coefficient. Okay, that's the only thing I'm adding. And if you see, Adaboost is doing something similar. Okay. Yeah. And the reason why I introduced forward stage-wise additive modeling is to say that Adaboost is doing above, okay, for exponential loss. Okay, so why is the statement not intuitive? I mean, so the reason why by just looking at forward stage-wise additive modeling, it's not clear if Adaboost is doing that, is because Adaboost is only manipulating weights on observations. Okay, it's actually changing the weights on observations. Whereas in forward stage-wise additive modeling, I'm not talking about weights on observations at all, right? I'm just saying find just the beta m and in the parameter of this function beta. Okay, so that's what this is saying. Whereas in Adaboost there is this weights business. Okay, and the way to reconcile that fact is to think of Adaboost is doing this forward stage-wise additive modeling for exponential loss. Okay, so if you assume the loss function to be exponential, so if you remember in forward stage-wise additive modeling there is this L, okay, this loss function. Okay, if we assume that to be exponential loss, then Adaboost is doing forward stage-wise additive modeling. Okay, that's the connection.
Can you repeat in forward stage-wise what's the difference between?
So this is a very intuitive model, right? I mean, let's say if I did not introduce Adaboost thing, okay, Adaboost, then this seems like a very intuitive model. I want a prediction model which is a composition of m basis functions or m functions. Okay, m classifiers, m regression models. Okay, and the way I'm going to build it is start with 0 function, add one function, which fits the data the best, and then that's in my bucket now. And that's in my bucket now. Then I'm going to add one more function, which that previous function is now frozen. So that plus this function is better able to predict y. Then I'm going to add the second function, and then keep these two functions frozen. Try to get a third function whose total sum is now going to predict y really well. Then get that list. So that's what forward stage-wise additive modeling is doing. Okay.
This could be used for ensemble methods.
Yeah, this can be used for any sequence of models that you want to have. Like for example, one of the b functions could be linear, another function could be decision tree, another could be something else. So given that I've already added linear in my ensemble, I can add a decision tree which is such that the linear plus the decision tree is going to better predict my y's. You can do all that. This is just a general template. But so for this general template, all you need to specify is this basis functions or whatever b's, which are parameterized by gammas, and you just need to specify the loss function. Okay, squared loss, for example. But if you look at Adaboost, should I show that Adaboost? Yeah. So there is a lot more formulas here. So let me just not show that. What I wrote here. So this is what Adaboost does. So it's basically manipulating weights. It's not doing forward stage-wise additive modeling. Okay, but it's still adding functions. Okay, if you look at the final function that Adaboost is supposed to get, it's a sine of sum over m is equal to 1 to m alpha m gm. Right. So this alpha m resembles the beta coefficients there, and gm resembles the b function there. Okay, it's just that the way it's getting to this is not really explicitly solving minimize over some loss. Okay, if you see steps 1, 2, and 3, there is a minimize over loss in the step 1, but that's not the same loss that you saw in forward stage-wise additive modeling. Okay. It's not weighted loss, first of all, and it's also not capturing. Okay, so I guess the key difference is here you're plugging in the previous model that you had, previous sum of m functions that you had is also a part of your loss minimization. In Adaboost, this step is not talking about explicitly the previous models that you have figured out so far, but it is implicitly capturing that through weights. Okay, that's the non-triviality. Okay, it's implicitly capturing the effect of previous models through these weights, and in forward stage-wise additive modeling, there is an explicit capturing of the previous models through this fm-1, which is just the models that I've already considered and put in my final solution so far. Okay, so that's the difference. And so if you just abstractly look at Adaboost, it's doing something, right? But you want to kind of reason statistically what it is doing, and it is actually doing forward stage-wise additive modeling with a particular loss, which happens to be exponential loss. Okay, that's the way to explain why Adaboost makes sense. Otherwise, it's not clear. I mean, intuitively, we are saying that it kind of scales up the weights of observations where we are making mistakes. That's intuitively correct. I mean, that's fine. But I guess this is yet another explanation of, tries to bring it back to the type of stuff that we are a little bit more familiar with. Because rescaling observation weights, we were not, was kind of a new idea, right? So this you must have seen in the other class, right? Not forward stage-wise additive modeling, but Adaboost, right? Any confusions about that? Yeah.
What do we mean by exponential loss?
Okay, so loss functions. That's a good question. So exponential loss is so we are still. Let's assume we are still in the 2-class classification setting. Okay, so that's where Adaboost m1.m1 is applicable for. Exponential loss L of y comma, just let's say a generic y and a generic f of x is just e to the power minus y times f of x. Okay, this is the loss function. Okay, so I mean, if you just want to write L of a comma b, if comparing two numbers, is just e to the power minus ab. And this only makes sense when so we said we are looking at 2-class example setup where y was taking a value in -1 and 1 and x was whatever arbitrary. So you can see, so why does this make sense? If f of x, it's a classification setup, so f of x, if it's positive, then you better want y to be +1. Okay, so if both are positive, then e to the power minus a positive term is something small. Okay, but if f of x is a positive number, so it's predicting a positive class, but y is negative, then the product of these two is negative. E to the power minus of a negative term is positive, so it's actually giving a high loss value. Okay, so basically you just want sign alignment. If f is positive, you want y to be positive. If y is positive, y is the data, yi is positive, then you want f of x to be positive in the same direction. And if y is -1, then you want f of x also to be negative. So then if the signs align, then there is a e to the power minus something which is almost close to 0. Okay. Whereas if the signs don't align, you have a e to the power positive term, so you're really kind of penalizing for not being aligned. Okay, that's what exponential loss means. Any other questions? Okay, so that's kind of partially explains why Adaboost makes sense, because I said forward additive, stage-wise additive modeling is roughly the template that Adaboost is following. When you kind of bring in exponential loss, and then you will see that the weights are kind of related to exponential loss and so on. But there's still one piece of incompatibility, which is fit GM given data and weights. I didn't really specify how you fit that. I mean, if it's a decision tree, you can choose your node impurity function and do whatever. So there's still a fair degree of freedom with Adaboost. So it's not completely explained by forward additive stage-wise modeling and exponential loss, because here your choice of loss can be arbitrary. Okay, so it's still a very difficult algorithm to kind of reason about. But anyway, if you're not confused about it, don't worry. So let's now. So the reason why I wanted to introduce that is to talk about gradient boosting. Okay, that's the kind of key idea for today's class. So before that, I'm gonna specialize. I'm gonna kind of fix the GMs to be equal to T m of x given theta m. Okay, so I'm gonna use this notation for a tree. So decision tree. Okay, so the mth decision tree is a function. Given an x, it has to produce a class, right? Let's call theta m the parameters of the tree, and the parameters, as you know, are just regions, right? R1 to R j regions, maybe jm regions for the mth tree. So m is the index of the tree now. So maybe this tree has m, R1 to rjm regions, and then maybe it has so depending on classification or regression, it will have, let's say it's classification, then it will have p hat m k. Okay, maybe not m k. A bunch of p hat k's. Okay, I don't want to index it. Okay, there's a lot of numbers. Okay, which describe the tree, right? So if you take the forward stage-wise additive modeling perspective, then at every step m, I'm gonna compute theta m to be the arg min over theta m's of sum over I is equal to 1 to n of the loss of yi minus whatever trees that I've already used. Let me call them, there's sum to be fm of xi plus the tree itself which I'm optimizing over xi given theta m. Okay, so basically this is the thing that we want to now find, right? The tree is the next tree, the mth tree is what we want to find. We've probably already added m minus 1 trees. Okay, and the way we find this tree is that the new tree plus the previous guys, whatever they're predicting, they're close to yi's. That's what we want. Okay, I mean, I just wrote the forward stage-wise additive modeling version of it, but in Adaboost, the way you get a tree is, again, you have weights. Okay. And you do a weighted node impurity function calculation. Okay? Just add the weights. So whenever you are doing let's say for regression, you're doing sum over yi minus some constant square. Instead of that, you do sum over wi times yi minus constant square. Okay, so weights just come in as coefficients in your tree computation. Okay. So given that, so that makes sense. So what is the so I can use Adaboost, and within Adaboost I can use GMs to be trees. Okay, that's what I just mentioned. But there's still a catch. Okay, and the catch is the catch is you can work with squared loss for trees easily, because then the coefficients are just averages of y's and so on. But if you just change the loss functions arbitrarily, then computing that Adaboost, the next tree which is best fits this loss function, for example, here, is hard. Okay. I guess not hard, but whatever, computationally difficult. Computationally. For example, if I change the loss to absolute value loss, then the problem is difficult. So the reason why the problem for squared loss is easy is because if you assume squared loss, then the C1, C2, like if I split a region into C1, C2, then C1, C2 just happen to be average of the entries. But if you change the loss to be something else, maybe for actually, what is that? Absolute value loss, maybe I think it's not the average, it's the median, I think. If you think of absolute values between the y minus c's. But for arbitrary losses, you can't really get, there's a computation step needed. Okay. And so that brings us to the idea of gradient boosting. Okay. And the idea is to recognize that, let's say I'm solving a problem, minimize over. I use the notation f vector, okay, of f vector, okay, because if you see, this loss function is a sum over of training data, okay, I is equal to 1 to n. So I'm going to define f vector to be f of x1 to f of xn, which is n cross 1 dimensional. Okay. So there's an n dimensional numbers. If I can plug in into my loss function, then I can evaluate the loss. Right? It's just a sum of yi and one coordinate of this f vector. Not the sum, but so sum of the loss of the difference, loss of these yi's and coordinates of this f vector. Right. So I'm kind of removing the dependence on the data, because data is anyway fixed. I don't want to touch it. Okay, and so I have a loss for an f vector, and the way to numerically optimize this type of a problem, okay, is to, so if you want to minimize this, okay, one way to do this is via gradients. Okay, what do I mean by that? You start with some f vector 0. Okay, if you have an f vector 0, you are at some point in your optimization space. You take the gradient of the loss function at that point. Okay, so let's say the gradient is called gm. G0. Okay, it's called the gradient. Okay, I can just, so given the gradient and f naught, I can say f vector 1 is equal to f vector 0 minus rho 0 times g0. Okay, so what's the high level idea? All I'm saying is, let's say you had a generic optimization problem, okay, where you are supposed to put in n numbers, right? I'm supposed to figure out n numbers, right? I have an f which is evaluated at n locations, xi, x1, x2, xn. So I'm supposed to put in n numbers. So let's think of those n numbers as the variables in my optimization problem. Okay, let's not think about the parameters of the function itself as variables in the optimization problem. Let's ignore that for a second, and let's think of these n numbers as things that I could set to minimize my loss. Okay, so I'm saying if you want to do this, let's think of an iterative procedure. Let's start with some n numbers f naught. The underscore bar just means I have n numbers, so these are all vectors in Rn. Okay, n dimensional vector space. Let me start with some starting point f of f naught, and make iterative updates such that after some time I get to the best n numbers that minimizes this loss function. So this is a particular way of optimizing any objective, right? I'm saying in particular I'm saying let me take an iterative approach. I start with some initial candidate n numbers, kind of add something to it so that I get another candidate of n numbers, and hopefully the next at those next candidate of n numbers, which is let's say f1, I have lesser loss value. Okay, L of f bar of 1 hopefully is less than L of f bar of 0. Okay, and so on. So I'm making basically I'm just describing gradient descent. So if you have already seen gradient descent or steepest descent, then this should be familiar to you. I'm saying to optimize any function, I can always take an iterative approach where I can keep on updating my starting point f of x naught with scaled versions of gradients so as to move forward in the search space. Okay, search space is these n numbers that I want to get, this n dimensional vector. Okay, so I just wrote one gradient step here. So what is the intuition behind gradient? If you have a function, okay, if you can evaluate the gradient of that function, okay, the gradient is going to be if you have some function, okay, let's say this is x and this is function of x. Oh, let me not use f. Some function of okay, let me use f here. Okay, let's say I started from here. This is a f of f naught. Okay, if I take the gradient there, gradient is just some like a hyperplane, or it's like a line segment, which is the first derivative of the function at that point. Okay, gradient, if you take the negative direction of the gradient, which is this, and update your point, you'll go to the lower location. Okay, take the negative direction and add that to your current estimate, so something like this. Okay, and then you'll get another point f1. So that is what I've written here. So this is f1, where I just arbitrarily added some row, but just think of it as if you have a function, take its gradient, travel to the negative gradient, add that to your current value of candidate, then you'll get another candidate f1, and that will have a ideally lower value. Okay, so this is called the gradient way of optimizing things, I guess, using gradient information.
So basically, gradient is just not a local derivative, or
yeah, derivative. And so the way it works is first you compute the gradient and then you figure out the optimal value of rho. Okay, what is the right rho to kind of minimize your objective, because you want to minimize this objective. Okay, this objective L of f bar, where f bar is a function of a bunch of f bar itself is a function of a bunch of parameters. Depends on, let's say if it's a tree. Okay, tree has a bunch of parameters. A given decision tree has a bunch of parameters. But if I evaluate the tree at x1, x2, x3, xn, I'll get n predictions, right? I'm thinking of these n predictions as the parameters for this problem. Okay, but they're all tied together because there is a single parameter for the tree which gives me these n numbers, and these n numbers are the ones which determine my loss score, right? So okay, just one more thing. Okay. So what we want to do is a general loss function L, and still work with trees. trees as weak classifiers, let's say. And the way we work with it, and the way we work with it is, I'm going to explain it through this particular, snapshot. Is as follows. Okay. So we want to work with the general loss function L. Okay. Now I'm saying I have a loss function L. I'm going to specify to you, and you still have to work in stages. So you have to still tell me at the end of the day, tell me a sum of m trees. Okay. That should be your output finally. Okay. But how am I going to add these trees to my collection? Okay. My solution, I'm going to get my solution incrementally, one tree at a time. How am I going to add these trees? And the gradient tree boosting algorithm does it as follows. It initially sets some some constant function. So think of this as finding a constant value such that that constant value, the loss of yi comma that constant value is the lowest. Okay. So this is a constant function. The first step is saying find a gamma such that my loss is the lowest. Okay. It's just a constant function. Okay. And then the next I'm going to do is find the gradient of my loss with respect to the function, which is going to be n dimensional at my previous function value. Okay. So if it's a constant function, all I'm saying is, so this function will give me n numbers, right? At the beginning of time, it will give me n numbers. I'm going to find the gradient of my loss at those n numbers. Okay, that will give me some gradient direction. Those are called, those I'm calling as RIM. I is from 1 to n. Okay, m is just indexing the stage index, so forget about it, not very important. So Ri, these are the gradient values, okay, or the negative gradients. So there's a negative sign here. Okay. Now the key step in gradient boosting is the following: is that you fit a regression tree to the targets, which are the gradients. It's gradients themselves. Okay. Giving some regions, if you fit a tree, you'll get some bunch of regions. Okay, that's not important. What is very critical here is that I have a general loss function. I start with some starting point. It just happens to be a constant function here. I compute the gradients of that loss function. I'll get n numbers. Now I'm considering these n numbers and solving a tree fitting problem. So these n numbers are my y's for my tree fitting problem. Okay, yi's were there, right? So yi comma xi was there. Instead of delete yi's, think of ri's as to be your data. So ri comma xi is your data for the tree fitting problem. Okay, so you're fitting the gradient using a tree. Okay, and then you know that I'm supposed to travel with some constant times gradient I need to add to my collection to actually do gradient descent or steepest descent. I'm gonna just add the tree to my previous model. Okay, the tree, because the tree is approximating the gradient, I'm gonna just add the tree to my collection of previous, whatever is the previous fm minus 1. Okay, so the key trick in gradient boosting is just to add, compute gradients and make the gradients the right hand side of your tree fitting problem, let's say a regression tree, and then get that tree and think of that tree as a gradient and add it to your collection of models. Okay, so you're adding models one by one, but you want to add a tree, but you only have gradient information, so you approximate the gradient and the excess with the tree. Okay, that's the key step, and everything else is just forward stage-wise additive model. Yeah. Yeah. Yeah, we are not doing that, right? M is still a parameter here. So at least in this algorithm, we are not doing that. We are saying keep on computing gradients, keep on approximating the gradients with trees up to m trees, and then keep on adding them to your collection. But in general, for numerical optimization, unrelated to this gradient boosting trees, yeah, you can kind of look at whether the gradient is flat or is it like, does it have a magnitude or not, something like that, and you can deal with it. But that's kind of yeah, so relative improvement in gradients or something is not large or something like that. Yeah, I mean, there's some terminating conditions for general numerical optimization, but here we don't care about that. Here we are just saying we want to do a gradient style update because we want to work with general loss functions, this L, because the tree itself will have its own internal loss functions, choice of the impurity stuff. Okay, that's how I'm constructing the tree. But I want to have a loss function L, which has nothing to do with the weak learners, the weak learners or the weak classifiers losses inside. Whatever kind of leads to, whatever leads to the optimization for the tree itself. I don't care about those loss functions. I care about minimizing, for example, this loss function. Okay. So that's the idea of gradient boosting tree. So the remaining is just straightforward. So the step C is just saying, given the tree regions, I want to compute the coefficients of the regions, right? Just like in the tree, once you have the regions of the tree, you also need to compute the coefficients. They are saying you have to recompute it because, it's not difficult. You just have to recompute it because it's a different loss function. The tree regions, the tree coefficients were computed because of node impurity functions, right? Whereas here, we want to compute it with respect to this loss. This is not difficult, okay? And then you just add that tree to your, this is actually a representation of a tree. You can just, we could have written as t of x comma, whatever theta m, and then you keep repeating this, okay? So that's the idea of gradient boosting. So generally working with arbitrary loss functions when you are thinking of sums of trees, okay? Any doubts? I'm sure there are lots of doubts. You're not supposed to understand it in one, few minutes, but you will kind of get familiarized with it over time. Okay. If you have any quick questions, just reach out to me after the class. That's it.